Abouzaid from Columbia, and he'll talk on towards odd symplectic Khovanov homology.
Thank you. So this is some kind of report on joint work, progress, very much in progress, with Michael Smith. And the starting point is a proposal of Witten and Gaiotto-Witten. For this kind of new point of view of Khovanov homology. And please don't ask me anything about it because, sorry, is it off? Oh. So anyway, so it's a proposal of Khovanov homology. And the only thing, so there's long papers and long explanations. And the only thing that I derive from it at the very end is that that from the point of view of Floer theory, what they propose Floer theory. Well, there are several proposals, but I think somehow, the one that I believe has a reasonable chance of working, from the view of Floer theory, they propose to study the Fukaya category of some kind of Hilbert scheme of points, let's say of M point on C cross C star, in fact minus some divisor. Okay, so let's call this space something like Z sub n, equipped with some potential. With some map Z sub n to C, potential. There's supposed to be M. Okay, and somehow the reason that you would want to do this, and then if you were to study some kind of Fukaya category associated to this potential, you would see the arc algebra and Khovanov homology and things like that. And simultaneously, because this space has the property that H2, this is some kind of computation, with Z coefficients is isomorphic to Z mod 2. Okay, so you do some computation, you see that there's non-trivial H2 class, you can then twist by this class. And then the twist is supposed to give rise to odd Khovanov. Okay, so in that sense, kind of the reason, I haven't been really thinking that much about Khovanov homology, but the reason I got back into trying to thinking about symplectic models for Khovanov homology is because we don't have a good geometric model for the odd theory, and this for once seemed like the first hopeful sign that there could be something to be done. And so the goal of this talk is to explain, is to basically tell you that the relation between this story and the symplectic Khovanov story that we already understand in the first non-trivial, in the first case, which is basically the case of C times C star itself, Hilb 1, so this space itself. And in that case, what is most interesting is that you don't need to understand anything about this Gaiotto-Witten justification to derive the existence of this theory. You just have to be comfortable with mirror symmetry. And so what I will start with is some kind of overview or explanation of kind of how we think about mirror symmetry these days, and what and how kind of by thinking about mirror symmetry for certain class of examples, you are led naturally to produce two spaces with the property that somehow the Fukaya category of these two spaces are somehow equivalent. And fortunately, the existence of this H2 class doesn't occur for m equals 1. It only occurs for m equals 2. Okay? So we won't be able to see this twist, but of course, kind of people who have thought about odd and even Khovanov homology know that there is no interesting twist for the unknot, which is basically what we're going to talk about. Okay? So let me say some things about mirror symmetry.
So they
Yes.
have a
Yes.
construction that just involves C as well?
Yes,
Right?
I'm 95% confident that it doesn't work. And it will show up. Let me get to it. So good. So what did I want to say about mirror symmetry? Oh, yes. So the way we think about mirror symmetry these days is as follows. And this kind of is some kind of modern reformulation of Strominger-Yau-Zaslow. And the goal of, from this point of view, what you want to do is you basically want to make mirror symmetry into some kind of tautology. So the starting point is supposed to be some kind of X, which is symplectic manifold, which is equipped with some Lagrangian torus fibration. And out of this data, if you have a Lagrangian torus fibration, then you can produce the space of object of the Fukaya category of X which are simple and are supported on the fibers. Okay? So imagine you take some kind of simple modules over some ring and you try to equip it with some kind of, think of it as like spec of that ring, and then it would come naturally with the structure of an algebraic variety. In this case, if you think about it a little bit more carefully, the only thing that naturally comes about, so let's call this Y. So this is some kind of analytic space. And this is the putative mirror. So the conjecture is that Y and X are mirror. And somehow the basic thing to say is to say, for example, so what's kind of specific consequence of claiming that they're mirror, e.g. you want to say that the Fukaya category of X, which is something about all Lagrangians in X, not just the fibers, is somehow equivalent to the derived category of coherent sheaves on Y. So this philosophy, this is somehow the right philosophy, but usually it's not the philosophy that is used when proving mirror symmetry, because it's very hard to control this idea of, understanding all the Lagrangians supported in fibers, all the objects of the Fukaya category supported on fibers. But for X equals to 2 torus, for example, which is equipped with this fibration over S1, if you run the story, what you get is that Y is an elliptic curve. And similarly, if you did this in one higher dimensions, which is the first case you'd encounter something kind of non-trivial, you try to do this, for example, for the K3 surface, and then you would really have to understand what is meant by objects of the Fukaya category which are supported on the fibers, because now there's some kind of singular fibers. Okay? But this is not the subject of today's talk, and the main reason it's not is because when you're studying these examples, this works very well for closed Calabi-Yaus, okay? But we're not going to be talking about closed Calabi-Yaus. We're talking about somehow Hilbert scheme of C times C star, which is of course not closed. So, so how to extend this? Beyond closed. And again, So this is somehow maybe something that was implicit in the physics literature, but the first time at least I've seen it stated very precisely in work of Ohu. Okay, and it goes in two steps. So the first thing you say is, first, the same story works if X is an open Calabi-Yau. Okay. So that above was assuming X is closed. Maybe implicitly I didn't write it down, but you just for X open it works. For example, if you give me X which is T star S1, so this has a Lagrangian torus fibration because it's just over R. Then you just apply this. You look at the space of local system, the space of objects of Fukaya which is stored on fibers. That ends up being exactly the space of fibers equipped with a local system. Okay, so the local system is a point in basically the dual torus, and so you end up with Y being a copy of C star. Okay, that's fine. And then the next thing you want to do is, assuming you've understood mirror symmetry for open Calabi-Yaus, if you had something that was not Calabi-Yau, you would basically cut out something from it to get an open thing and try to understand what is the procedure of putting something back in. So the mirror. So if if the holomorphic volume form on X extends to, let's say, X union some divisor to have a pole of order 1, pole of order 1 along D, then what should happen is that the mirror of X union D is going to be the same space Y, but now equipped with some function, let me call it W sub D because it depends on D, to C. And this W sub D, it counts whatever that means, holomorphic disks. Can I erase this higher? Oh, very good. Holomorphic disks with boundary on the fibers, on the torus fibers of X. Okay. So, for example, so since I'm doing that case, what I can do is I can take X to be R2, which you can think of as T star S1 union a point. Okay? And so that point, let's say it's over here. And so once you add this point, let me just make it like that. Every fiber bounds exactly one disk. And on the mirror side, what you get is that the mirror is the potential Y equals C star going to C by the function Z. And if you know something about symplectic topology, you know that somehow the Fukaya category of X is basically 0. There is no interesting Fukaya category of R2 if you don't equip it with some extra structure. And this, usually, people say that this corresponds to the fact that the critical set of critical points of this function Z is 0. It's empty. Okay? But just to illustrate the fact that things are kind of a bit delicate, if you instead took D to be 2 points, so if you take X union D is equal R2. If instead you make some other thing which is slightly larger, 2 points, which is going to be kind of CP1, let's just say S2 instead of CP1. Okay? So which is, again, T star S1 union 2 points. Then now, if you take any fiber, it bounds a disk on this side and a disk on this side. Okay? And if you keep track, the point is that this monomial, the fact that we got a z here is just a statement that if you took the boundary of this disk, it wraps around this torus fiber once in the kind of clockwise direction if you give it an orientation. Now, if you look at this picture, this disk winds around in this direction, but the other disk goes in the other direction. And so what you get is the mirror to S2 is the same space C star, now with the function z plus z inverse. And if you compute the critical locus of the function z plus z inverse consists of 2 points, which I don't want to compute what they are. And what that means basically is these 2 points under mirror symmetry go back to the equator inside S2, equipped with two local systems. So this story that I'm telling you kind of, it works extremely well in examples like S2 or toric varieties or something like that. And so what I'm trying to suggest here is that this story that I'm telling is going to allow us to produce, to see that kind of some potential on C times C star is somehow equivalent to something on T star S2. And the key point is like this. So we have this X union D here, which is mirrored to Y with some potential, but that, the presentation of this potential depends on writing this compactification as an open part union in the divisor. Okay? If this were also some kind of X prime union D prime, okay, for some other X prime and other D prime, another way to say this, if these two partial, potential compactifications, or let me say partial compactifications, happen to be symplectomorphic, then this guy would also be mirrored to some other Y prime equipped with some other W prime to C. Okay, and then you would get some non-trivial, some non-trivial equivalence between something about this Y and something about this Y prime, and they wouldn't know anything about each other. They would just know about each other because it so happened that they came from the same mirror, from kind of different mirror pictures on the same space. Okay, but unfortunately for what we need to extend this story a little bit more, and I'll just put it in some kind of box here. So we can extend this a little more. And so it's not just Y that we can consider. We can also take a hypersurface on this side as well. So by taking a partial compactification of Y, so you take basically Y union H. Okay. So before I was partially compactifying the symplectic side, but I'm saying you can also partially compactify the B side, the complex side. And this, as expected, is mirrored to some kind of potential on X. X to C by some potential, which has the name H on it. Okay? But then you could go further, and this is somehow the thing that is really relevant. You could take this partial compactification, and you could equip it with some function. Let me just, I don't want to give specific names anymore. I'll just call it W. Okay? And then this would be mirror to X union D equipped with some potential, let's say V to C. Okay? So the slogan is that compactification on one side, so compactification or partial compactification on one side corresponds to introducing a potential, in fact, just a term in the potential for the mirror. But what I'm trying to say here is that you could do both things simultaneously. On one side, you could both, like if you try to partially compactify both sides, and you'll introduce potentials on both sides. Okay, good. So now comes the specific example, which I claim has some relevance to this problem. And the example is, I'm going to start with y. Okay, so the other thing I should say maybe is that oftentimes the story can be run backwards. I've been treating X as a symplectic manifold and Y as a complex manifold, but you could just go the other way as well. So we're going to be interested in the Fukaya category. So I'm going to, in Fukaya category of X, so I have to start by talking about Y. Is that I let Y be, well, yeah, that's a good question. What exactly is Y? Yeah, let's do it like this. So let me start with something, let's call it Y bar. Okay, so I want to set Y bar to be the resolution of the A1 singularity, A1 surface singularity. Okay, so let me be more precise. So that is that you take C2 mod Z2, that's a singular fiber, so this is the A1 singularity. And then if you basically blow up at the origin, you get A1 tilde, which is our Y bar. So the point is that there are, so now we want to study mirror symmetry for this. And so to analyze it, what we have to do is we have to try to find a good torus vibration and so on and so forth. And there are two approaches. So there's kind of two nice ways of producing the mirror. So the first is that you take, let me just call it 1 actually instead of 0. So you take the divisor D. No, let me call it H because we're on this side. You divide the divisor H, which is given. Okay, let me give this by this. We give some coordinates here. This is called S and T. Okay, so inside here you take the equation given by ST equals 1. Okay, and of course you can mod this out by Z2. The singularities of this Z2 action occur at the origin, so this lies away from the singularities. So this is away from the singular point. So this basically gives a conic in Y bar. And then what you can do is you can, I'm not going to do this one explicitly, so you can produce, and this is explained in some work of Uru and also in some work of mine and Uru and Katsarkov. So you can produce an SYZ vibration, a torus vibration. And then you can dualize. So you can run this picture that I've been sketching here, SYZ. And the outcome of this procedure is going to be something like X, which is T star S2 minus another conic. Okay. And so again, you can write down formulas for what I mean by T star S2 minus a conic, but the main thing to do maybe is to draw a picture. So the picture is that if you think of T star S2 as being the locus of UV equals W squared minus 1 inside C3, then you can project to the W coordinate. Okay. And then there's going to be two critical points. This is the W plane. This is a +1 and this is -1. Okay. And then this conic that I want to remove is just given by the locus where W equals 0. So you basically remove this point. Okay. So this is almost the space. So if we put we fill the fiber over 0 back in, locus W equals 0 back in, we get the space, the first space that shows up in the Seidel-Smith or Mendelescu approach to Khovanov homology. Okay? Because that's basically T star S2. But here I told you what so why would you want to fill it back in? The reason you want to fill it back in is if you look at this space itself, roughly speaking, there is more. So in T star S2, there's a unique Lagrangian sphere, unique S2, and this S2 is going to be what's associated to the kind of basic only object of the arc algebra when they're for the first arc algebra, and then if you kind of pair it with itself, okay, you get the Floer cohomology of S2 with itself, but that's exactly the ordinary cohomology of S2. So this is kind of the rank 2 vector space that shows up in Khovanov homology. And if you don't do it, if you don't fill it back in, then you're in some kind of annular situation. So otherwise, this is kind of an annular theory. And by that I mean somehow that there is this sphere and there's this other sphere, okay? And they're not actually equivalent to each other, so there's some kind of an extra grading coming from the kind of going around this divisor that you removed. So anyway, so what that means, going back to what I'm kind of suggesting here, is that if you really just want the Seidel-Smith space and you don't want this annular theory, what you then do is you put in some kind of potential on sorry, where are we? On y bar minus h. So T star S2 is nearer to some potential on y bar. Okay.
Question?
Yes.
If you, in this annular picture, so you're saying if you take the two objects in the Kukai category corresponding to those two curves, and you compute the Floer.
Yes.
Is it two-dimensional, just with a different gradient?
Yes, the Floer homology between them is two-dimensional, but the products are not. Well, so once you have a puncture, you have to kind of figure out you have a choice on what you mean by degree, because you have a bigrading. You have a homological grading and you have a grading by this. And in Floer theory, kind of the homological grading is not canonical. You could add to it any multiple of this grading. So, but I mean, the way that I would say it is, if you don't have this, there's a morphism here in one direction and a morphism in the other direction whose product is the identity. Okay, but if you pull this out, the product is 0. Okay, so that was the first picture. And now in this picture, kind of you just see this S2 that corresponds to what shows up in Khovanov homology. And now I want to talk about the other picture, which somehow physicists have known about for much longer. And the other picture is about just choosing another anti-canonical divisor in some sense. Okay, instead of choosing, roughly speaking, instead of choosing this one, ST equals 1, you just pick ST equals 0. So use ST equals 0. And then what I want to point out is that this is invariant under the C star squared action on our original space. In fact, on C2. I mean, everything just descending from C2. On C2. So we call this the toric anti-canonical divisor. So let me call it H prime. Okay. Now the complement of H prime is, well, you can just look at it here. I take C2, and I remove S equals 0 and T equals 0, which means I get C star squared, and I mod out by a Z2. But that's just another C star squared. C star squared mod Z2, which is again C star squared. Okay? So you could be worried. I mean, I haven't quite said what H prime is, because I'm being slightly ambiguous whether we're working with the H prime that lives in the singular space or in the resolution. And indeed, I have in mind the one in the resolution. But if you're looking at the complement, it doesn't matter, because the only singularities of this space are at 0. That's the only singular point, and that lies now on my hypersurface. Great. So this will be our y. Y prime. Let's call it y prime. Good. But I've mostly used C star squared. And so then, we're now in a toric situation. So toric mirror symmetry is kind of extremely well studied. And it's easy to write down what the mirror is. I mean, I already told you here, if you see C star, the mirror is just T star S1. The same is true here. So the mirror of y prime is, again, so I should really say, given what I was doing over there, x equals T star S2, T star, sorry, S1 squared. But there's really no difference. I mean, I'm just going to allow myself to identify T star S1 with C star, because we're going to be writing a potential on it, and it's better to have some kind of algebraic coordinates. So the mirror of y prime is this, and then the only question is, what is the mirror of H prime? And the mirror of H prime is some Laurent polynomial. Okay? And now, if you know any toric geometry, you can just derive it for yourself. But so I will just, I don't want to tell you how to derive it, because will take us a little bit too long. It's the Laurent polynomial W equals x plus y plus x squared over y. Okay. In fact, we're in a moment we're going to change coordinates. So maybe what I can say is that if you know any, these are, if you know any toric geometry, you can write down a fan that controls controls y, and roughly speaking, these are the vectors, the primitive vectors of the fan. Okay, I'm a symplectic topologist, so I actually think in some kind of moment picture, and the moment picture for A2 looks something like that. And in this case, these guys are the dual, this is kind of x, and this is y, and this is kind of x squared over y. Okay, you go from, so that corresponds to the vector -1, 2, -1, which is the normal vector of this facet, and the rest you can figure out. Great. Now I want to do something really boring. So, I mean, really, really elementary. I want to compute the critical point of that function. So by now you all should have done it already. So dw equals 1 plus 2x over y times dx plus 1 minus x squared over y squared times dy. Okay? That's dw. I think I did it right. And now you set this equal to 0. And then there's no solution. I'm not going to do it. Now you can just say no solution. Okay. I mean, this basically says x and y are related by like 1/2, and this says x and y are related by √1. There's no way it can happen. That's a problem. Because remember, when I tried to give you this toy example for why the Fukaya category of C is 0, I said, well, we all know the answer. Because on the other side, the critical locus of this function is 0. So this suggests, so if you are, if you kind of think that Fukaya categories of potential functions are studied in Paul Seidel's book on Lefschetz fibrations, you open up the book and it says, look at the critical points and build these thimbles, and well, there's no thimble, there's nothing. So this cannot be studied using Seidel's, thimbles, whatever, Fukaya category with objects thimbles. Anyway, if you know something about this. This is part of the reason why it's good to have precise names, and when people tell me like the Fukaya-Seidel category, I never know what they mean. So to me, this is what it means. You take the thimbles and you build some objects that generate it, and that just doesn't apply here. So what that means is you have to go back to maybe the first thing that Kontsevich said when he introduced these things. So go back to Kontsevich's suggestion for the Fukaya category of a space equipped with a potential, okay? And you just don't assume it's a Lefschetz vibration, because this has no critical point.
Wouldn't working equivariantly on C2 mod Z2 also help?
Would working equivariantly...
That would introduce some extra logarithmic terms in the potential. And that usually gives it critical points. Yeah,
but I wouldn't know what it means, kind of. I mean, I think I know what you want to do, but it's, literally, this interpretation is the reason there's no critical point can be made mathematically precise. On this side, there are no compact Lagrangians with with the correct behavior with respect to Flirt theory. Another way to say this is, I wouldn't want to do that. And again, the story of mirror symmetry, I've been saying it one side gives you the other, but actually you can go the other way as well. So now you could ask me, what about the Fukaya category of Y, of this A2 resolution? Okay, and then the Fukaya category of this A2 resolution is trivial. There are no non-trivial. There's no Lagrangians with non-trivial homology. Now the equivariant Fukaya category may be non-trivial, right? But that's somehow another question. Okay, so suggestion for this Fukaya category of this potential, and I'll just draw a picture. So his suggestion was, if you have some space equipped with some potential over C, then what you should study are Lagrangians in X, so that when you project them, you get something such that the projection goes in the positive real direction asymptotically. Okay, and the statement is not completely precise. This is the right thing to say if this projection is proper, and in our case, a projection is not proper. But that somehow, this is kind of a general class of Lagrangians we should study, and it makes some sense to think about what is the Floer theory for them. So this is if X to C is proper. Okay, and one way of producing these things, and essentially as an outcome of Paul Seidel's work, we can basically prove that, in the case of Lefschetz vibrations, if all the data at infinity is kind of sufficiently well controlled, the one way of producing these are, if you have critical points, you can draw arcs emanating out of these critical points, okay, and these are the thimbles. But sometimes these have all the Floer theory that you're looking for, and sometimes they don't. Okay? And this is a case where either the story about mirror symmetry I told you completely breaks down, and this space is just completely uninteresting. Okay, this space with this potential is completely uninteresting, or somehow there are other interesting objects that don't come from critical points. Okay, and it's the latter. Let me ruin the surprise. Okay. Erase. So we have to figure out some other way of thinking about the geometry of the space and of this potential, really. And so it has no critical point, so you have to find something else. The thing to simplify your life is to actually change coordinates. So I actually can prepare this talk. And so what you can write is that W can be written, so I'm just going to factor something. Okay, so you can check that that's correct factorization. Let's remember that x and y is in C star, so I'm allowed to divide. So if I just set u equals to x squared over y and v equals to y over x, then this is the same as u1 plus v plus v squared. Okay? So once you see this, of course you could have seen it for some other ways, you see that w is C star equivariant for now the action which is, having done this change of coordinates for the action which has trivial weight on v and weight 1 on u. Weight 1 comma 0 on u comma v. Okay. C star equivariant to weight 1. So that then implies that the only critical point, well, no, sorry, there are no critical points. So what that implies is that all fibers away from 0 are isomorphic. Okay? So what I do to remind myself that I'm going to do something which doesn't involve a critical point is I'm going to draw a disk, and then I'm going to put a little square here. For this funny singularity, it's really some kind of singularity at infinity. That's why there's interesting Floer theory. To look at the time. At some point, I want to get to Bigelow's Lagrangians, so I have to check the time. So anyway, so this is the fiber at 0, and there are fibers away from 0, and if you can now analyze it fairly quickly. So the fiber at 0 is, well, this times this is equal to 0, okay? But u is not allowed to be 0, okay? Because we're working in C star squared. So that means that you have a copy of C star, let me just say u, the u coordinates on C star, cross the zeros of this function. So this is 2 points, hopefully, yes. Okay? Let me draw it. Let me draw it here. 2 cylinders. Okay. What about the fiber away from 0? The fiber away from 0 is, well, if you're away from 0, you can project to the v plane. So project to the v, to see a v. And what you can get, because u basically appears with degree 1 here, so you get the complement of the 0 locus. Get complement. Oh, here I should say C star v. Get the complement of this 1 plus v squared equals 0, which means, let me now draw it some other way. So and maybe the best way to draw it is like this. So this is 0 that is missing. This is the v plane, and these are the 2 roots. The 2 roots of that polynomial, whatever that is. They're probably not here, but it doesn't matter. Okay? So it's almost, okay, so basically it's kind of, let me draw it slightly differently. Good. So now we have at least some understanding of the geometry of this space. The general fiber is a 4-punctured S2, and there is some special fiber which is 2 cylinders, and then the first time you encounter this, you think, how do these things possibly fit together? Okay, it doesn't seem reasonable that you could have such a vibration, but I just wrote equations, and clearly you can do it. Let me explain in a second what you do to think about the geometry. But before doing that, I want to go back to, part of what I was discussing here. On the other side, we also have this potential, okay? Because we needed this potential in order to get only one S2 instead of 2 of them. I don't want to do the annular. So if we want to do the annular theory, this is the space we should study. But let's not do the annular theory. So, because it's going to simplify our lives. So okay, I could use the same words here. So we want to introduce a potential on the mirror, which means on this side, we want to partially compactify. And if you think a little bit through, well, you have to do some kind of computations. So introduce potential on mirror, which means partially compactify. But this is kind of we're going to do the nicest possible partial compactification. And we're just going to partially compactify the C star V to a plane. Okay? And that's why I kind of switched to these coordinates. Kind of these coordinates make it very suggestive that that's what you want to do. I got rid of all divisions, of all negative powers. Okay, so if you partially compactify, what ends up happening is the fiber away from at 0 doesn't change at all. It's still exactly this, okay? Because it was, the solutions of this polynomial in C star and in C are the same. But now this fiber, you fill in one of the, let me just do it somewhere else. So now we end up with this picture. So here we have 2 fibers, and here we filled in one of the punctures. Okay? And the way now this picture is supposed to be suggestive, because this is infinity in the C plane, and these are the 2 punctures, the two zeros of the polynomial. Let me write just P of V equals 0. Okay, and this, which are missing from this fiber, and this is basically P of V equals 0 times C star U. Okay, and what you should imagine now is that if you're on this fiber, and if you're on the general fiber and you're moving towards 0, what happens is that you kind of grab this kind of saddle point, and you push it down to infinity. You push it down to infinity, and what you're left with are these 2 cylinders. So these 2 cylinders kind of match up with these 2 ends. Okay? And this one just kind of disappears out of existence. Great. Now, as I said, we want to build some Lagrangians in this space, and they should have the property that they have. They behave cohomologically like S2s. And so the techniques of this kind of Lefschetz-Seidel techniques for using critical points don't work, so we need something else. And if I had time, I could motivate this other thing using mirror symmetry as well, but it's going to be basically impossible to do that, given that I only have 15 minutes. But what I will say, what I will say is that basically what we want to do is we want to start with Lagrangians in the fiber and turn them into Lagrangians in the whole space. The idea, and maybe the correct thing to say is this is due to Orloff in the context of trying to understand kind of how mirror symmetries for Landau-Ginzburg models and mirror symmetry for fibers of Landau-Ginzburg models are tied in together. So the idea is that there is a functor from the Fukaya category of a fiber, and what you want to imagine is the fiber is really far at infinity, so I'm going to just put that. Okay, even this is kind of some abuse of notation, to the Fukaya category of our space, I guess it's just called X, equipped with potential W. What is this functor? This functor says, take a Lagrangian inside of this fiber. So in our case, this is just a pair of pants. And then do something to it so that it looks like one of those things that Kontsevich tells you you're allowed to study. Okay? But that's pretty obvious what you would do. You would just take that fiber here, and you would move it around all the singularities of the fibration. So this is the Orloff functor. Parallel transport. Let me just say, you could do something much simpler. You could say, why would I go all the way around? Why don't I just, for example, do this? You could do that. It would give you a perfectly reasonable Lagrangian, but it would be a trivial object of this category. Okay? You don't want to do that. This thing kind of, it kind of encapsulates non-trivially the fact that this vibration, while it has no critical point, is still not a trivial vibration. It's not a trivial map. Okay. So then the remaining thing to do is to ask oneself, which Lagrangian should I use, and what would their Floer homology be? Well, in order to answer that, we should understand the Fukaya category of the pair of pants, right? Because that's somehow what everything amounts to. So this is an extremely well-studied subject, being the first non-trivial case after the cylinder. And basically the thing to do is so now unfortunately there's two perspectives. There's some kind of perspective using closed Lagrangians and some perspective using open Lagrangians. Let's start with the open Lagrangians first. So what you want to do, and the object we're going to care the most about, is just this arc connecting these two punctures. Okay? And the Floer homology from this arc to itself can be computed. Well, it looks like there's nothing, but in fact what you should do is you should perturb. And you should not just perturb, you should kind of follow the flow here that goes around like this, and the flow here that goes around like this. Okay? So this is how you define Floer cohomology of the arc with itself. Okay? And if you compute, what you get is that somehow this guy here is 1. And then here, as you go around, you get generators, let's call them y to the k, for k greater than or equal to 1. And as you compute here, you get a generator called x to the k, for also for k greater than or equal to 1. And if you try to multiply x by y, you get 0. Okay? So this is a ring. Well, whatever your coefficient field is, coefficient ring is. So that's okay. So that's some kind of the computation of the Fukaya category of this pair of pants. I mean, there are other things we could compute. We could talk about the arc that goes from here to here, the arc that goes from here to here. In some sense, they generate, but we're not going to use them. We're only going to use this Lagrangian, and then if I have time, there'll be one compact Lagrangian that will also show up. Great. So then, having done that, I should explain how you compute the Floer homology of what happens when you apply the Orloff functor. Okay. But this, again, there's some kind of general formalism. So let me actually draw it instead of just appealing to it. So if you draw this picture, and now I take this parallel transport, and I try to compute the Floer. Let's say this is, let's call this functor something. Let's call it O. Bad name, but anyway. So this is O of L. Okay? And I try to compute the Floer homology of O of L with itself. Then this recipe, which I didn't talk about, which was in this kind of luscious vibration world, is that you take this O of L and you move it down. Like this. Okay. And then you compute, let's call this O prime of L. And then you compute the Floer cohomology of O of L. O prime of L. And that's the correct morphisms in this category. But if you stare at the picture a little bit, you see that there's only two in the base, there's only two intersection points. Here and here. And at these intersection points, you get exactly the Floer homology you had before. So let's give this a name. This is some ring, R. Because what I'm doing now is some kind of completely general computation. So you get some ring R. And here you get the same ring R. Because you're just doing Floer homology in the fiber. Actually, that requires the monodromy to be trivial. But anyway, in this case, that's what happens. And then the only interesting differential is some map from here to here. Some kind of differential from here to here. And that differential, you can check that the map R to R that's part of the differential is just multiplication with some element. Multiplication with some function. Okay? So we just have to identify which function appears when we try to build this. And then what I want to say is these x's and y's, they correspond exactly to going once around these punctures. But these punctures are exactly the ones that are filled in over 0. Okay? So a little bit of work shows that in this case, f is actually equal to x plus y. So you end up with taking the cohomology of, so the map is this, so this is the complex. So that means the cohomology is just the quotient of R by the ideal generated by F. So HF star is just R mod F. And if I took this ring and I modded that by F, that is exactly a two-dimensional ring, which let me just now write K. Let me use some, I'll just use one of these variables, even though some abuse notation. Okay, so either x or y can be our generator, and that's this is the ring. Oh yeah, great. So this is what I said I was looking for originally. This is a vector space V, or if you want to say this is the cohomology list. Okay, so what I'm trying to suggest here is that so Tudor had some question about, like, in Gaiotto-Witten at some point apparently there's some kind of further reduction where instead of trying to do Floer theory in some kind of Hilbert scheme, you end up doing Floer theory. You're trying to do some kind of count. I mean, they don't do Floer theory, but they try to do some kind of count in a Riemann surface or a symmetric product of a Riemann surface. Roughly speaking, this is the first case. Okay, but then what I'm saying is that this doesn't give the right answer. You can get the right Euler characteristic from it. In the last 5 minutes, I will say something about that. But it won't give you the right cohomology group. At least from our point of view, it gives you this kind of very big ring, and then you need to quotient by some relation to get what you want. So now now I want to point out some interesting features. Remarks. So the first remark I want to make is that Ivan and I struggled a lot to produce a second grading on symplectic Khovanov homology, and we didn't even prove that it was a second grading. We just kind of built something which probably is, and it's kind of non-trivial to check that it's invariant. So kind of, let me say it like this: the bigrading on symplectic Khovanov is mysterious. But here, I haven't said what the higher dimensional generalizations of this is, and in part it's because I cannot at the moment precisely say what I expect it to be. But it's in this, somehow. These are the building blocks, but how you put them together is not clear yet. But anyway, the bigrading on symplectic Khovanov is mysterious, but here it's completely trivial. It arises from the fact that H1 of C cross C star with Z coefficient has rank 1. Okay? So there is the homological grading, and then there is an additional grading, which is how many times what is your winding number again around the unique homology class in this space. I mean, this space, again, we compactified. We used to have C star V. Okay, then we compactify that to C of V, but the other variable is still a C star U. Okay, so we have a C star U here, so we have a winding number around that. So this is one thing so we've lost something. We used to have a clear and obvious, easy to study Lagrangian, which is just the S2, and we made it extremely complicated, because to compute its cohomology now involves taking the quotient and doing some Floer theoretic computation and so on and so forth. But one thing you gained is that you can see the second grading. The second thing to say is that this is related to the Lorentz-Bigelow picture for the Jones polynomial. And by that I mean the following thing. So they had some picture where I'm just going to do the first case. What you would do is you would have some points on the plane, and then you would draw some figure eights around them, and then you would draw some arcs around them. Okay? And then you would think about the intersection between arcs and figure eights. And out of that you would produce the Jones polynomial. What we can do in this case is you could think of this figure 8 as itself as an object of the Fukaya category. So I don't have any time to say this, but if you do it appropriately, if you put in the right data, you can put yourself in a situation where the Floer cohomology of the figure 8 with the figure 8 is isomorphic to the Floer cohomology of the arc with the arc, and it's also isomorphic to the Floer cohomology of the arc with the figure eights. Okay, so you have these kind of isomorphisms here. So instead of doing arcs, which maybe don't like non-compact Lagrangians, you could do figure eights. But the main advantage of this is that, you know, in the Lorentz-Bigelow picture, there's the kind of this asymmetry between the figure eights and the arcs. And in our world, we can basically replace that. I mean, you can just basically say you'll either work entirely with figure eights or you'll work entirely with arcs. Okay? And you can define the Floer homology group, and you know, you can basically see that it has the right features to maybe now say something kind of weaselly, to admit a differential so that you get Khovanov homology back. Now, how you exactly define that differential when you have more strands, that part is still not, there's no theorem there yet. Okay, I should stop.
Questions?
Yeah, maybe.
Yes.
So in this picture, the gradient is very clear from local system on configuration space. So you cannot follow this gradient in the picture.
Let me think exactly. So in this is like in the punctured plane, right?
Yes.
So one thing that's going to happen is you're going to have to. So this, in this sense, here you can have a grading by kind of as many z to the n, where n is the number of punctures. And one thing you need to do is you need to collapse that to only one copy of z.
Yeah, but this is quite clear.
Yeah, that's quite clear. And yes, and the answer is yes. The weight grading, you just follow this grading. And you basically what happens is, yes, I mean, you know, this differential is, once you collapse it to 1, this differential that you get from these pictures is compatible with that grading. So that's why in this story there is a bigrading. It's in the original symplectic story that we don't know how to produce it. Well, that it was kind of very delicate to produce. But here is some kind of nice geometric thing. Yes?
How does this change for SLN homology?
No idea. So for SLN homology, right now, the only symplectic candidates we have are from the point of view of the original Seidel-Smith point of view, which is some kind of nilpotent slices. Okay? And so Ciprian has some paper where he considers the correct nilpotent slice for SLN, but there's, of course, no proof. But here, what I'm really using is that Ciprian has a picture where he takes Seidel-Smith's SL2 point of view and turns it into Hilbert schemes of points on complex surfaces. Okay? And this, to me, is kind of in that spirit. So I wouldn't know how to do SLN right now. Yes?
Related, does the Hilbert scheme that you're considering, does it admit a multiplicative quiver variety description? Or?
I don't know the answer to that. I mean, I should be able to, but I mean, this kind of Hilbert scheme on this complement of this divisor on the Hilbert scheme is kind of has appeared many other times before. It's some kind of space of monopoles, but I haven't thought about whether it has. I haven't seen. Nobody's told me that it has a quiver description. How about that? Yes.
Does it have any chance to generalize to knots over surfaces?
I haven't thought about that. You mean somehow surface times S1?
Yeah.
Yeah. I think somehow maybe Ellie would be the person. I mean, people. Sorry, people who thought about like annular stories might have a better idea than I. I've only thought about S3. Yeah. Yes.
I mean, this is only. You only talked about the unknot.
That's right.
Do you understand, for example, where the spectral sequence, the Heggard-Floer of the double branch cover should come from?
No. So I can say right now what we basically are pretty confident we can prove stabilization, and Handel slide seems to require some kind of some different insight. My guess is that Handel slide requires some insight that is already in Gaiotto-Witten, except that the formalism of Gaiotto-Witten is not very good for me to implement in symplectic topology. That's somehow the issue we have. The naive things to do symplectically, to do more strands, doesn't seem to give the right answer, and instead what they suggest seems to be closer to the right answer, but to implement it seems to just to be kind of technically difficult. So yes, I mean, it would be very nice to see this double branch. I mean, in the original Seidel-Smith picture, it's kind of fairly apparent. Yeah, and here, I don't know. Yeah, I don't know. Yes?
I mean, I always thought of odd Khovanov, like, again, I mean, you didn't talk about the twist, but I mean,
Yes.
I always thought of odd Khovanov homology as looking more like H star of S1.
Oh yes, should talk about the gradings. The gradings are insane. So if you, yeah, that's the thing. The gradings here, that's why we have a bigrade. So we have this bigrading, and if you actually look just at the homological part, I mean, roughly speaking, there's what I think of as the homological part. The part that comes from Floer homology, the part of the property the differential is degree 1, and then there is the weight part. And if you look at the homological part, you have actually quite a lot of flexibility in changing it. So it's not, I mean, you know, you cannot really say that something is weight 1 or weight 0 until you specify, you know, which sum of homological and weight you're going to use. So so kind of just in the geometry here, there is some kind of, there's this x and this y, and really there is no reason for them to be even. You could have had them odd. You're completely free to make them odd. And the reason you're completely free to make them odd is, roughly speaking, that the Euler characteristic of, you know, if you can kind of change the degrees here at the cost of changing the degree at infinity, but you're never using this infinity anyway. So that's why you have this flexibility of making it even or making it odd. So that's somehow one appeal of this picture that the other one doesn't.
All right, thank Mohammed again.